first of all, thank you for coming to my talk. Also, thank you for the organizers. This is my first time at GopherCon. It's absolutely amazing. I've been part of the Go team at Google for about 3 years, maybe a little bit more, and I work on the security topics. In particular, I've been working on Go's vulnerability management. And this talk is about vulnerabilities in Go binaries in cloud containers. So I would like to kick off this talk by asking you a question. If I told you that 50% of Go binaries in cloud containers are vulnerable, how many of you would believe me? You can raise your hand if you believe me. Okay, that's the vast majority. I apologize. This was a trick question. You were right in the sense that a lot of binaries are vulnerable, but those who actually kept their hand down, you are technically correct because that number is 80%. So in this talk, I'll be presenting how do we get to that number and what can we do to bring this number down. So I split this talk in 2 parts. First is about data, tables, and charts, where I'll be showing you the results of our experiments where we actually went deep into the real-world cloud containers that look to Go binaries. I'll be showing like Go versions that we use to build the binaries, vulnerabilities. And then the second part of the talk, I'm going to talk a little bit about the tools that we can use to actually secure ourselves. So I'm talking about the Scalibur and govulncheck, which are the 2 tools developed at Google for vulnerability detection. First, I would like to talk about cloud containers. So when I say container, what do I mean by that? It's very simple. It's just a Docker container. Second, I want to look at cloud containers. So we're going to look at Google Cloud Containers because the natural connection between the Go team and Google. So for this experiment, ideally what we would do, we would look at publicly available cloud containers that are most popular. Publicly means that if you have access to Google Cloud, to the artifact registry, you could in principle just access them. Most popular would mean that these are the containers that have been sent the most requests. They've been tasked the most. However, that last part is really hard to get, so we're going to approximate it by the number of metadata manifest requests. So basically, whenever you do a Docker operation, you're going to essentially make a manifest request. So the first data set that we collected is the top 1,000 publicly available Google Cloud containers and most popular by this notion that I mentioned. We call this set 80 because this is like all time. Of course, we want to measure the trends, how they change over time. So we're going to introduce RT, which is similarly, but these are containers created this year. So this is RT here stands for recent times. So what we did was very simple. We used Docker pull, Docker create to extract the contents. So here are some results. Basically, we can access 93% of these containers. Some containers got deleted in the meantime, they got private in the meantime, or they had some issues, so we just couldn't access them. And by the way, one thing I want to mention is that there is about 230 containers that are present in both of these sets. Okay, so we have the containers, we have the contents. Let's look at the Go binaries. So there is about 4.5K Go binaries in each of these sets. This means that on average, there is about 5 Go binaries per successfully analyzed container. But of course, a binary can appear in multiple containers. So from this point on in this talk, I'll be focusing on unique binaries. And these are unique up to their checksum. As you can see, there are more unique Go binaries in the AT set than the RT set. My hypothesis is that some Go projects just established themselves as leaders in certain area, and now the Go developers are actually using them rather than using some other alternatives as well. What's very important also here is that we can see that these binaries are present in about 70% of the containers, so which means the Go binaries are used heavily in Google Cloud Containers. Of course, because we have overlap in containers, we're going to have overlap in binaries as well. Here's where things get very, very interesting. What were the Go versions used to build these binaries? First, let's start with the AT set. Here's the pie chart. I'm going to take you through this step by step. The first thing I'd like you to focus on is the red part. This represents all unique Go binaries built with a Go release that's 1.17 or older. Goes back to sometimes to 1.4 or 1.6. So these are Go binaries built with a literally ancient version of Go. Moreover, if you start from the red part, you go counterclockwise all the way up to the blue part. That represents all unique Go binaries built with a Go version that is not maintained anymore. As you're probably aware, the Go team maintains the current major Go release, the one previous, but not anything before that. One also thing to point out is that on top there is Go 123 RC, that's release candidate, which means that some cloud developers actually really care about using the most recent Go version. But in general, the story is not very good. We have around 70% of these binaries built with a version of Go that's not maintained anymore. Okay, but that's for the AT set, right? How about the RT? Have things changed over time? Things are better, somewhat. We still have the red part, and again, counterclockwise all the way up to the blue. That's still more than half of Go binaries built with a version of Go that is not maintained anymore. Which means that cloud developers very often use a Go binary, they build it, they don't look at it for a long time, and if there are some vulnerabilities disclosed in the meantime, they're not being addressed. Okay, can we measure that? Yes, we can. How are we going to do that? We're going to use govulncheck. So govulncheck is a vulnerability detection tool developed by the Go team. I've been involved with this project from the outset to this very day. This is a tool that is able to analyze your source and your binaries, but what really makes it special is that it analyzes it at the level of symbols. So it's not just going to say, hey, you're importing a vulnerable package, or hey, you're requiring a vulnerable module. Actually, what it's going to do is the following. For source code, it's going to build a call graph of your whole program. And it's going to try to find, does there exist a path from entry points of your program to the vulnerable symbol? And if so, it's going to actually communicate that call stack. And for binaries, which is perhaps more important for this talk, we're going to look at the symbol table of your binary. We're also going to try to detect inline symbols. And if any of them are vulnerable, we're going to tell you that. Of course, none of this would work if you didn't have a vulnerability database with those symbols. So the Go team designed and is curating a Go vulnerability database. govulncheck has been around for a while now, and we've been working really to integrate it into different points. So right now we support JSON output, Serif output, and OpenVex as of recently. Here is how this looks in general, the command. You can tell it, scan things at a symbol default level. You can also be package a module if you really want to do that. You can say analyze, binary, source code, or there are three more options. And you can also format the output. By default, you get a human readable text, but you can also output JSON, Serif, OpenVex, and so forth. Here is how this looks, invoking govulncheck as a binary. By the way, I don't want you to go through all of this. The whole point is that you pass it some package patterns, it does some work, and these parts in rectangle are basically summarization of call stacks that it finds for you. You can also use govulncheck as a library. Actually, we designed it in a way that mimics exec.command, so it's pretty straightforward to use. I won't be going into the details of govulncheck in this talk because a colleague of mine, Julie, last year presented this in depth. What's important is that we use this tool, we run into all unique Go binaries in these containers. Here are the results. What this means for AT. So by the way, in parentheses, I'm just showing the number of unique Go binaries so you have it as a reference. So what this means that in AT set, 80% of Go binaries, we were able to find at least one vulnerable symbol. So it means 80% of these Go binaries are vulnerable. That's how we got to the slide at the beginning of this talk. Things are not much better for the RT set as well. In matter of fact, if you would run govulncheck with all these cloud containers, it would basically flag more than half of them as vulnerable. That's not good. Now you might wonder, okay, what kind of vulnerabilities did you actually detect? Well, they were mostly Go vulnerabilities. That's not surprising because for two reasons. Number one, we just saw that these Go binaries are built with the ancient Go version, so they're going to have some vulnerabilities. And also the Go team really cares about vulnerabilities. It accepts security requests, it patches them and releases in the next version, and also discloses the vulnerabilities publicly as CVEs, so tools like govulncheck can pick them up and inform you. So the next thing we wanted to do is like, okay, but suppose that we rebuild these binaries with the most recent Go version. Would things go away? Of course, we can't rebuild them all. We just don't have the power to do that. However, we can do a very similar thing. We can tell govulncheck to pretend that they were actually fixed. Basically, we tell govulncheck, forget about standard library vulnerabilities. Assume they're fixed. So what are the results? The results are much better, right? So now we have, by the way, there's still a lot of unique Go binaries here that are vulnerable. So these are like third-party dependencies. But we dropped from 80 to 20%. Of course, we're going to still, some containers are going to get flagged with this. But the whole point of this, if we would just rebuild our binaries, whenever a new Go release is published, we would significantly improve the health of our Go binaries and cloud containers in this case. This is way easier said than done, because you need to pay attention. How is the Go team releasing a new Go version? If it is, okay, now I need to set up a task for me to update all my binaries. It would be great if we had some tools to do that. So that's the second part of my talk. How can we do that? For that, we're going to use a tool called Scalibur. This is another tool developed at Google. It stands for Software Composition Analysis Library. It's written in Go. It is open source. You can take a look at it and contribute it. For folks who are familiar with OSV scanner vulnerability tool, they're merging their efforts together. What's cool about this tool is not just designed for Go. You should work on various different artifacts going from .NET, Java, and so forth. What I really like about Scalibur personally is it has two components. It has extraction and detection, which means it can analyze your container or your file system and extract security inventories and store them somewhere. But you can also pipe them to detection capabilities to actually check for vulnerabilities. Comes as a binary in a library. And here is, and by the way, of course, govulncheck is one of the detectors, not surprisingly. So here is how you would invoke Scalibur. Again, you don't have to go through all of this by yourself. I'm going to take you step by step. At first, we just invoke Scalibur saying, use all extractors, all detectors, and just save result to some text proto file. Scalibur says, OK, I'll do it. Here, I'm going to run 25 extractors, 4 detectors. I'm going to start from this directory and go recursively down. Then some output. I'm going to say, OK, I succeeded. I found more than 5,000 inventories, more than 150 security findings. I'm going to save results to text proto. This is how you would use it as a binary. Now, I want to show you how to use it as a library, but I'm going to take this a step further. What's really cool about Scalibur is that you can actually build your own plugins, which means you can define your own extractor and your own detector. And actually, what I'm going to do here is I'm going to task myself with building a tool that can actually tell you, does your container or your file system have any Go binary not built with the most recent release of Go? So basically, this should be a minimal viable product you can use in your processes. OK, let's first define our extractor. What is an extractor in Scalibur in general? It's an interface. It has a name. It has a version. That's pretty straightforward. It has a file required, basically stating, should this file even be considered for extraction or not? And then also has the extract method that takes a scan input and then produces some inventories. Has some other methods as well, but they're not so much important for this talk. OK, let's look what is a scan input. It's a simple struct. Path to this file, the scan route where we started our search, some information about the file, and reader so we can access the contents of this file. So that's the input. What is an inventory? Not much more complicated. It's a struct. It has a name, has a version, all the locations where this inventory was extracted from, the actual extractor that extracted it, and also the most important thing, the metadata. This is any information you want to extract from your binary, so that's why the type is any. That's all we need to know about extractor in Scalibur. Now we can define our own extractor. So what is our extractor going to extract? Just one simple thing, the Go version used to build the binary. OK, I call it Go version extractor. Not a very creative name, but it will do. The name is go/version. The actual version of this extractor, I just put it 0. You can put whatever you want. The file required is very simple. It's basically saying that I'm going to extract inventories, not for directories. We're going to go in directory recursively, just for files and symbolic links. And I'm just going to focus on executables. So all those executables are going to be passed to the extract method. Again, extract method takes an input, produces some inventories. So it's very simple here. The most important part is this API, so read.exe. It comes from an RSCIO Go version package. This is a package developed by the Go tech lead Russ Cox. What it can do is going to extract the Go version information from pretty much any binary, even those ancient binaries being built with 1.4, 1.6. So what we do here, we take this path of our Go binary, we pass it to read.exe, and if this returns an error, then that means basically we don't have a Go binary, we can just continue. Otherwise, we're just going to create one singleton inventory. What is going to be metadata? The Go release used to build this binary. And the location is the location of the inventory. That's it. We are done with our extractor. Now we need to define detector. The thing that's actually going to check is that Go release the most recent or not. In Scalibur, detector is very simple. Also, it has a name, a version, has required extractors. Basically, Scalibur uses this to pipe appropriate outputs from the extraction phase to the detection phase. It's very simple. And then the scan method. The most important thing about the scan method is it takes a list of inventories called here inventory index and produces some findings. let me introduce you to what is a finding. I'll take you step by step. It has an advisory. This is basically like something like CV or GHSA, right? It has some details about the inventories at which this finding was created, some extra information, and of course, detectors that produced it. So let's look at advisory a little bit more. It has an advisory ID. This is very simple. It has a publisher like CVE, and a reference is the actual CV, like CV 2024-15. What else has advisory? Has type, which is pretty much always going to be vulnerability in this talk. Has a title, description, recommendation, what to do when you see this vulnerability, and also severity. That's pretty much all we need to know about detectors in Scalibur, and we can now build our own detector. Here it is. I call it Go Latest Checker. Again, not super creative name. Has just one field, latest Go. This is where we're going to store the most recent version of Go. Name, Go/latest, version 0, and what is the required extractor? It's just one, Go/version that we defined in the previous slides. That's all. Now, scan is the most interesting method. It's very simple. To be honest, the hardest thing for me here was to actually present it in a clean way. So I'll just try to expanding this function as we go. So what do? First, we create some findings that we're going to resolve. We're going to return at the end, and then we're going to range through all inventories in the inventory index. That's why we use the method getAll. Give me all inventories. OK, so what do we do with an inventory? Let's focus on the code here in this rectangle. First of all, we get the actual Go version to use to build this inventory. That's our metadata, casted to a string. Now, also what I want to do, I want to check is that version valid. Version package here is the actual standard library package. So I'm going to check that the version is valid. And then I'm going to compare this version with the latest version of Go. Note here that I'm using greater or equal, not just equal. Why greater? Because I'm fine if somebody uses a release candidate. That's OK. If this Go version is valid and new, things are fine. This binary is perfectly fine. It was built with the latest release of Go. Otherwise, we have an issue. So we should create a finding. First, let me just create an advisory. The advisory is very simple. We're going to create some advisory ID. We don't have any particular CV in mind, so I'm just going to satisfy the API here. I'm going to say publisher none. I could have put whatever. And reference, I'm just going to create some generic name for it. But it really doesn't matter. What is the type of this vulnerability, of this finding? It is a vulnerability. And as a recommendation, I'm just going to say, please rebuild this binary with the latest version of Go. It's really simple Go code. The last thing I want to do for the advisory, though, I want to create also a good description. Here's the code. First, I'm just going to branch. Very simple. If this binary was not valid, I'm just going to say that. You build this with invalid Go version. Otherwise, you build it with a non-latest Go version. So now we can create finding. Here it is. Advisory is just the advisory we created, and the target is the inventory at which we found it. We store it to a list of findings, and we return it. So that was our detector. Now I just need to stitch things together in a main. That's all. First thing I do, I create a new Go latest checker. That's going to be our detector. I'm going to show the code for that in just a second. But basically, I need to ask the Go command to give me the latest release of Go. After that, I create a Scalibur configuration. So what I'm telling Scalibur here, please use as a scan route, use the current directory. So basically, start scanning from this directory downwards recursively. As an extractor, note we are using Go version extractor. That's the thing that we defined in previous slides. And detector is this checker I just created. And then we just pass this configuration to a new instance of Scalibur. We get some results. That's our invocation to Scalibur. Let's process the results. OK, so I'm going to skip the code where you check for failures because, honestly, it's quite boring and we don't really have time for it. But basically, what we do here is say, hey, if there are no findings, that means all of our Go binaries are up to date, and we just return 0. We're good. Otherwise, this is a very simple Go code. I'm just going to print all of those binaries that we found that have issues and basically print description recommendation. So one thing you'll notice that I'm returning exit code 3 here. So when we develop like analysis tools in Go, we reserve 0 for OK, 1 when something is wrong, really wrong with our code or the user's code, and 3 when everything is fine, but we discover something the user should inspect. That's our main program. The one thing that I owe to show you is to actually how do we figure out the most recent version of Go. This code, the most important is this, is go list. So we pass to go list, toolchain at latest, and that is going to give us some information. The rest of the code is just parsing the JSON. It's really not particularly interesting. Once we parse it, we take the version from the go list and we save it as latest go. That's it. This is all the code that you need for this tool. I built it, I called it, again, non-creatively Scalibur plugin, and I run it in an actual real-world container. Here are the outputs. It said, I found 3 outdated Go binaries, and then it lists information for all of them. Let's just look at the one at the bottom. So basically what it's saying, I found CLI binary. It was built with non-latest Go version 1.18.3, and recommendation is please rebuild this with Go 122.4. That was released earlier this month. That's all. This is a minimal viable product. You can, in principle, use it. It was that easy. So Scalibur is very powerful. The team is adding more detectors, more extractors as we go. They're providing more output formats, etc. So I highly invite you to check it out. Also, if you have any questions about vulnerabilities in general or containers and findings, please talk to me, because we have way more findings than this talk can fit. And as a summary, I'm just going to repeat what we found. Basically, a lot of cloud containers have outdated Go binaries, and they have a lot of vulnerabilities, a lot. And we should address this somehow. And we have govulncheck and Scalibur as tools that can help with that. That is all, and thank you so much.